All right, so now let's return back to the definition of the convergent sequence and we'll think about it for a moment. So let's recall that the sequence Sn converges if there exists an S in R such that for every epsilon greater than 0, there also exists a capital N in R such that Sn minus S is less than epsilon, and in that case, that means that the limit n goes to infinity of Sn is equal to S. Right, so basically the sequence converges if it has a limit S. If I think about this definition, then one, not really a problem, but deficiency, if you want to prove convergence, the deficiency is that in order to prove convergence by using a definition of a limit, you have to know what S is, right? Because somehow you have to show that this difference must be less than epsilon, and if S is not available to you, then it's impossible to prove if a sequence converges or not. On the other hand, it is kind of clear that I should be able to describe a convergent sequence without identifying a limit. What I mean by this is the following. If the sequence converges to some S, that means that the terms of a sequence eventually become arbitrarily close to S. And basically what the definition says, starting from a certain capital N, all Sn will differ from S by no more than epsilon. Which means that if I compare two Sn's with n being bigger than capital N, let's say, for example, if I know that S20 and S51 are less than 0.1 from S, then the difference between S20 and S51 must be less than 2 epsilon, just by the triangle inequality. So then it would appear that I should be able to demonstrate convergence of a sequence by being able to demonstrate that starting from certain capital N, the distance between two elements of a sequence with indices larger than this capital N is going to be smaller than epsilon. And this brings us to the definition of a so-called Cauchy sequence, which we will show for real numbers essentially will end up being a convergent sequence. So let's give the following definition. Suppose that for a sequence Sn, given any epsilon greater than 0, there exists an n in R such that Sn minus Sm is less than epsilon if both n and m are greater than capital N. Then we call the sequence Sn. Cauchy. Cauchy sequence. All right, so this is precisely what I just said when I discussed convergence. The sequence convergence if all elements of a sequence eventually are going to be epsilon away from the limit S. And for the Cauchy sequence, for any epsilon, eventually all terms of that sequence, starting from a certain capital N, are going to be different from each other by no more than epsilon. And all right, let's do a couple of examples. Example number 1. Let's suppose that Sn, in fact, show that Sn equal to 1 over n is a Cauchy sequence. How can I do this? Again, we will use the same strategy as before. Let's suppose that we have an epsilon which is greater than 0. What do we want? We want that Sn minus Sm should be less than epsilon. Okay, so but what does that mean? Sn minus Sm is, in this case, 1 over n minus 1 over m, right? Then by triangle inequality, this should be less or equal than absolute value of 1 over m plus absolute value of 1 over m, which is actually 1 over n plus 1 over m. And now I'm going to suppose out of these two numbers, one is going to be smaller. So let's suppose that m is smaller, so that m is less or equal than n. And then we continue this set of inequalities, Sm minus Sn minus Sm is going to be less or equal than 1 over n plus 1 over m, right from the previous line. And now, because m is less than n, if I replace n by m, I'm going to make this expression larger, so less or equal than 1 over m plus 1 over m, which is 2 over m. And I'm going to request that this is less than epsilon. So 2 over m less than epsilon, that is equivalent to saying that m is bigger than 2 over epsilon. And I'm going to call capital N my 2 over epsilon. All right, so then if n is bigger or equal than m, and both are bigger than capital N, by following the chain of inequalities that I've written above backwards, we have that absolute value of 1 over n minus 1 over m is going to be less than epsilon. And so we're done, so that means that this sequence is Cauchy. Notice that I'm writing here n greater or equal than m. Again, if I have two terms of my sequence Sn and Sm, I'm always free to interchange the index. I can call Sm Sn and Sn Sm. So that means that I always can assume this relationship that I circled on the screen right now, simply by interchanging the meaning of the index. All right, so the sequence 1 over n is a Cauchy sequence, but we also know that 1 over n is a convergent sequence. So then, next I would like to show that actually convergent and Cauchy would mean the same thing. And so let's do a theorem number 1. Theorem 1. Suppose that the sequence Sn converges. Then Sn is also Cauchy. And the proof of this fact is actually not so complicated. And it will rely on the definition of convergence and on the triangle inequality. So what do we have? Since Sn converges, for any epsilon greater than 0, there exists a capital N such that Sn minus S is less, and I'm going to use epsilon over 2 here, and it will be clear when I'm using I am using epsilon over 2 in a moment. If n is bigger than capital N, right? Again, in the definition of convergence, definition of a limit, I can always put whatever number I want here. Okay, so then suppose that m and n are both bigger than capital N, and consider the difference Sn minus Sm. How close is Sn to Sm? Oh, I don't know how close they are, but I do know that both are close to S. So rather than comparing Sn to Sm, I want to compare both of them to S. And I can do that by adding and subtracting S inside the absolute value sign. And then using a triangle inequality to have that this is less or equal than Sn minus S absolute value plus S minus Sm absolute value, but that's the same thing as absolute value of Sm minus S. And because both m and n are bigger than capital N, I have that the difference between Sn and Sm and S must be less than epsilon over 2. So this is less than epsilon over 2 for Sn minus S. And likewise, Sm minus S is less than epsilon over 2 because M is also bigger than capital N. So plus epsilon over 2 equal to epsilon. And again, I'm done because I assumed that the sequence converges, and I verified that the sequence also satisfies the definition of a Cauchy sequence. Okay, so any convergent sequence is Cauchy. All right, let's do one more theorem. Theorem number 2. Or let's just write it this way. Suppose that I have a sequence Sn that is Cauchy. Then from this I will conclude that the sequence Sn is bounded. And this result should be reminiscent of something that we already proved some lectures ago, and that is any convergent sequence is bounded. So the proof should look similar. All right, so let's suppose that Sn is Cauchy. And I'm going to fix any epsilon greater than 0. So I'm going to choose epsilon and fix it to be some number. I can fix it 1, I can fix it to be 3.1, whatever, right? So use your favorite number and fix it as epsilon. All right, so then by definition of the Cauchy sequence, so definition of Cauchy sequence, there exists a capital N in R such that Sn minus Sm is going to be less than epsilon if both N and M are bigger than capital N. All right, so we have that. So then, let's choose. So if we choose M to be capital N plus 1, we have that Sn minus S capital N plus 1 is less than epsilon for any n bigger than capital N. Why? Because M equal to capital N plus 1 is certainly bigger than N. All right, that's good. So then it follows that if I remove the absolute value sign, it follows that Sn minus S capital N plus 1 without absolute value sign is less than epsilon and bigger than minus epsilon if n is greater than capital N. Add Sn plus 1 to both sides. Sn plus 1 minus epsilon less than Sn less than Sn plus 1 plus epsilon if n is bigger than capital N. And from this, we now conclude that Sn plus 1 minus epsilon is a lower bound on the set Sn n is bigger than capital N, right? Because this relationship is true for any n which is bigger than capital N. So that means, and once I fix capital N, Sn plus 1 is a number, epsilon is a fixed number from the beginning, so the circle thing is a fixed number. And likewise, S capital N plus 1 plus epsilon is going to be an upper bound on the same set. So, and Sn plus epsilon is an upper bound on the same set. Okay, so then that means that the tail of my sequence is bounded both from above and below, respectively, by these two numbers. Okay? Fine. So then, what if I look at the set? So now consider the set Sn. So I'm considering my sequence as a set. When n is greater or equal than 1. What is the difference between the two sets? So this guy contains all terms starting from capital N plus 1. And this guy contains all terms starting from from 1. So that means that this set is going to be a subset of this set. And if it is a subset of this set, then the upper bound on the set starting from n equal to 1, what can happen to the upper bound? Can it become lower for a larger set? No, right? Because as we discussed this before, the upper bound on a larger set automatically has to be larger. It cannot be smaller than an upper bound on a subset. Because subset is already contained in the set itself. So that means that the upper bound on the subset is the least that the upper bound on a big set can be. And then what is the difference between larger set and a smaller set in this case? The difference is the first capital N elements. So then how large can an upper bound on the circle set can be? It should be larger than an upper bound on a subset. And it should be larger than any of the first capital N elements. So if I take a maximum of the first capital N elements and an upper bound on this subset, then I should get an upper bound on the entire set. So, if we consider this set, then the maximum of S1, comma, S capital N, and the upper bound on the subset is Sn plus 1 plus epsilon. This is an upper bound. On Sn n greater or equal than 1. And a similar consideration I also would say that if I take a minimum of these guys, if I take a minimum of the first n elements. If I take a minimum of first n elements and the lower bound on a subset of the larger set, so we can repeat exactly the same arguments for the infimum, right? If I take a subset of a larger set, then a lower bound on that subset should automatically be greater than the lower bound on the entire set, because entire set contains more numbers. If those numbers are larger than the numbers in my original subset, then the lower bound will not change. If they're smaller, then the lower bound will become lower. What's the difference between the subset and the set? It's the first capital N elements. So the minimum of the first capital N elements and the lower bound is going to be a lower bound on the entire set. So minus epsilon, it's a lower bound now, instead of plus epsilon. And then you get a lower bound. And so then the conclusion is that the set Sn n greater or equal than 1 is bounded both from above and below, and thus it is bounded. Right, and so therefore Sn n greater or equal than 1 is bounded, and we're done. All right, and then in the next installment of this lecture, we're going to prove the result which was opposite to the theorem number 1. So we know that any convergent sequence is Cauchy, and we want to prove that any Cauchy sequence converges. And that's what we're going to do next time.